All right, hello everyone. So today we're going to work with a trigonometric substitution problem here. We're trying to find the antiderivative of the quantity x cubed divided by the quantity radical or square root of 4 minus x squared dx. All right, so using a trigonometric substitution, typically the way it's done is by looking at the form that you have. And I wrote some forms with some square roots here. And yeah, so you have the form of a square root of a squared minus x squared, square root of x squared plus a squared, square root of x squared minus a squared. Now you actually don't need to have the square root there necessarily. However, that's the most common way of presenting these. So in other words, if you have something of the like, you have a squared minus x squared plus a squared, x squared minus a squared, you can use these substitutions here. Okay, let me actually write that word in on top. And the key here is to look at your expression involving the squares and asking yourself, what does this most resemble? Well, if you look at that expression, that would be that square root of 4 minus x squared here. Your substitution would be this a sine theta, okay? So as I said, that's what, going further, that's what I wrote here. So in our case, we're gonna say square root of 4 minus x squared, and that's equal to saying 2 squared minus x squared, right? 2 squared is 4. So your substitution is gonna be x equals 2 sine theta. Now, what do I mean by a substitution here? So what you're gonna find is you find your x to be 2 sine theta, and you're gonna need something else, the differential dx, which is simply the derivative. So dx equals 2 cosine theta d theta. We add that d theta. And what I'm gonna do with that integral is I'm gonna substitute that x and dx, okay, in there. And that's what you see on this next step. So, 2 sine theta to the third power. That's how I get that 8 sine cubed theta. That dx is right here. And when we replace the x with a 2 sine theta, you square that, that becomes 4 sine squared theta. Okay. Now, on to our next line right here. Use my highlighter for this. If you look at the square root, I factored a 4 from the square root from this previous step right there. And the reason I did that, because going to the next line down here, you have 4 times cosine squared. Why? Because under that square root, because 1 minus sine squared is equal to cosine squared by the Pythagorean identities. Okay, and that's usually what's going to happen with these problems. With you're doing a trig substitution, you're going to work with one of the Pythagorean identities. So cosine squared plus sine squared is the most famous one probably, but you also have a few other ones. So I would take a look at those, but let me just write, there's 3 of these. Secant squared theta equals 1 plus tangent squared. And then you also have cosecant squared theta equals 1 plus cotangent squared. So those are your 3 identities, and that's what you're going to be working with in some form or fashion, with these problems. Okay, not so much the third one actually. When I think about it, it's mainly these 2. Anyways, so we have that identity, and what I did on this line going from here to here. Now let me erase all this stuff. Is I went ahead and took the square root of 4, which is 2, and you have a 2 cosine theta. Okay, and all I did here from this line to the next was canceled out the cosines and the 2, and you have that expression left. Now, how do I go about solving this part? When you get to this integral, when you simplify everything out, you usually will use, there's a bunch of techniques that you can use. One, in this case, what we're going to be using is a trigonometric trigonometric integral. That's one technique. You also have a see here, trigonometric integrals. You can use a substitution. Often the case is that you have something along the lines of a cosine squared or a sine squared that's left over for your integrand for the inside. And you would use the substitutions 1 plus cosine 2 theta over 2, or 1 minus cosine 2 theta over 2. And the other thing that I've seen that's actually a little more common than these two is you're going to use trigonometry to simplify, and in particular identities. To simplify integrand and integrate. Okay. So now what we'll do is this. So what we'll do now is rewrite sine cubed as sine squared theta times sine d theta. And I'm using this technique of trigonometric integrals, which says if you have an odd power here of sine or cosine, take one out. So this is what I mean by take one out. So you pull out one sine and you have two sines left. And what you're going to use is you're going to use a trigonometric identity, sine squared theta equals 1 minus cosine squared, or Pythagorean identity. And the way it works is you're going to do a u sub. And you're going to let u equal cosine theta. And then your du here would equal negative sine theta, d theta. And this would rewrite as 8 times the integral of 1 minus u squared times negative du, or negative 8, 1 minus u squared du. That's negative 8 u minus u cubed over 3 plus a constant. And I'm going to replace my u here with cosine theta. So that'd be cosine theta minus cosine cubed theta over 3 plus c. Now, we are not done, unfortunately, because I have cosine theta instead of an x. Started with x's, I want to end with x's. So how do I go about doing that? Well, let's go back to your substitution, x equals 2 sine theta. Another way of writing this would be x over 2 equals sine theta. And if you think about it, and this is, well, I'm not a mathematical historian, so I don't know, but I think this was the motivation for these substitutions, or partially this was how it was looked like in terms to solve this. You have x over 2 equals sine theta. So think about a triangle. Let's say you put your angle right where I put it. Well, sine is equal to opposite over hypotenuse. So that tells me this side over here could be x, and this side could be 2, or any multiple of 2 and x. And this side down on the bottom by the Pythagorean theorem would be 4 minus x squared. Square root of 4 minus x squared, excuse me. So if I found the cosine of that angle, that'd be the square root of 4 minus x squared all over 2. And what we'll do is rewrite every cosine that I had up here with that. So you would have minus 8 times the square root of 4 minus x squared over 2 minus 4 minus x squared to the 3 halves all over 3 plus your constant c. Okay? And if you distribute that negative 8, negative 4, right, and all of this right here just means take the square root and raise it to the 3rd power. Okay? And you would get this as your final answer. Okay. So once again, trig substitutions work out really well when you have something of the form of what you see here in blue. And yet you don't have to have exactly the square root. You can actually get rid of it, and these substitutions would work out pretty well. But yeah, typically we have them on there. And you basically take your substitution to according to what the form you have, and you find what your a is. That's just a number. you let x equal blah, 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 and then you find your dx and you substitute. And you're gonna simplify, you're gonna use a lot of Pythagorean identities when you're doing these. And you'll reach a point where you're gonna integrate something that you know how to integrate. That's one of the points here of this method. And as I said, mainly it's either a trigonometric integral, or you get to the you get something that says cosine squared or sine squared. You can use those identities, or you use a little more trigonometry to simplify the integrand. And in this case, we use a trigonometric integral here to solve. And at the end of the day, though, you can't forget that you have to plug things back into x. So that's where your substitution comes back in handy here. And yeah, all that substitution was so you can integrate a little easier, that's it. Or, sorry, not easier, but you could integrate. And you use that substitution, you write out, a triangle, and that's how you can get the other trig functions in terms of x, like we did. And there you go. All right, thanks for your time.